So let's talk about the reactions of our unsaturated hydrocarbons, particularly our aliphatic ones, the alkenes and alkynes. So there's a lot of reactions to learn, but if you understand that every single one of them is going to follow the basic pattern of an addition reaction, it can be really helpful. So what is an addition reaction? So we've learned about substitution reactions where one atom or group of atoms substitutes another. In an addition reaction, we're not substituting, we're adding to. So an addition reaction is one where one molecule or groups of molecules combines to a larger one, so it's added to. And all of the different alkene, alkyne reactions, these unsaturated hydrocarbons, all of them are addition reactions. So even though it can feel like a lot, they all follow the exact same pattern. And here's the generic pattern here. And we're getting rid of all the extraneous stuff so that we can just focus on what's the pattern of the reaction. So we have the double bond here, or if you want to view it through a model, the double bond there, or sometimes I like to use my hands and be like, here's the double bond. And we add across the double bond. So we have some reactant that we're adding to it. And we're going to look at lots of different things we could add to it. But what happens is that double bond, I kind of think of it as it opens up like a drawbridge. Now you'll notice the single bond, a single bond remains. So the double bond turns into a single bond. So the two carbons don't separate from each other. What they do is they open up, and then jazz hands, they have room to grab onto something new. One can grab onto whatever the A is, and one can grab onto whatever the B is. And that's the addition reaction. Or if we wanted to look at it through a model kit, I have the double bond here, which tend to be less stable and therefore more reactive than single bonds. So if it opens up, let's see if I can do that, snap, satisfying snap. If it opens up, so I still have a single bond between the carbons, but now I have room for each of these carbons to bond to something new. So we lose the multiple bond and go back to having a single bond in its place, which is going to change the geometry of the substance, and it's going to change a number of factors, especially depending on what we add. Now, all of those different types then that you are learning about or are about to learn about really come down to not the pattern of the reaction, but this question: what are we adding to it? So let's start with a blank board and very generically and say, okay, here, here in the middle of, well, my little pen's having issues. In the middle of my board, I have my alkene. Now I'm going to probably focus on alkenes, but the truth is that we could just as well focus on alkynes and have that triple bond in there. So just a lot of this information you have to go like, or an alkyne. So depending on what we add across this double bond, depending on what we add to the two jazz hands across the drawbridge, that's what's going to distinguish what kind of reaction it really was. So if we add, for example, let me change colors. If we add water, if we add a water molecule, and we'll look at what that looks like in a sec, across the double bond, we are doing a hydration reaction, which kind of makes sense. We're hydrating it. So that's one of our possibilities. If we are adding hydrogen across the double bond, hydrogen gas across the double bond, so a hydrogen here and a hydrogen there, we are hydrogenating it. So hydrogenation. You can actually see the word hydrogen right there. So that's another type. If we are adding a halogen, such as like bromine or chlorine or fluorine or iodine, and of course these are diatomic, so that's really what we'd be adding, one to each side, we are halogenating it. So halogenation. So that's another option. But they all do it the same way. They all open up the double bond, the single bond stays between, but now this carbon can grab something and this carbon can react with something. We could also do it with a hydrohalogen. So hydrogen that's bonded with bromine, or hydrogen that's bonded with fluorine, or hydrogen that's bonded with chlorine. And so that type of reaction that we could add across the double bond is called a hydro, for the hydrogen, halogen. So hydrohalogenation. So the reaction of adding a hydrogen and a halogen across the double bond. And another thing that we can do is we could actually add another unsaturated a hydrocarbon, especially another alkene. So we'll just say unsaturated hydrocarbon. And that is that addition polymer reaction, which have a couple different names. So we'll say addition or polymerization. We're running out of room. Now, a little squiggle. Now that can look like a lot. We've got 5 different reactions here, and I sometimes call them the Furious 5 because of that. Hydrogenation, halogenation, hydration, hydrohalogenation, or self-addition, also known as polymerization. But all of these follow that same exact format of an addition reaction, where we have these 2 carbons with a multiple bond between them, and that can be a double or a triple, and they stay single bonded together, but the double or multiple bond opens up and grabs onto other atoms. So it adds across, and there's no other product. They're not, as opposed to some of the other reactions we've seen where there's an additional product. Here, we're adding to the molecule to create something more. And we tend to then end up with a more saturated hydrocarbon than when we started with, either fully saturated now, because they're all now single bonds, or maybe we went from a triple to a double. So all of these, we see an increase in the saturation because that multiple bond is lost or reduced. So here is a diagram I like from a textbook that looks at them as well, kind of in the same way that we were just talking about. It depends on what you add that changes the type it is and is going to create a different product. This one doesn't include the self addition, but we could, if we wanted to, we could add that to the diagram as well. If you add another alkene, your product is a polymer of the alkene, and you get that 5th of the Furious 5. So a thing to note is these first 2 are what we call symmetrical addition reactions. And that word means exactly what you think it means. It means you're adding symmetrically across that double or triple bond. What that means is you're adding the same thing. So what this jazz hand grabs is the same as what this jazz hand grabs. And you're going to see that. So for example, like when you have, we're adding hydrogen, we're adding a halogen. It's a BR, I can't see it. So both carbons that were of the multiple bond are going to grab the same thing. And that's where that word symmetrical comes from. These 2 are what we call unsymmetrical. And so that means that you can probably predict what it means. It means one carbon is going to grab one thing, and the other carbon of the multiple bond is going to grab another. So there's an unsymmetrical addition across the double bond. So for example, with hydration, we're going to see that one carbon grabs a hydrogen and the other grabs the hydroxyl group, is what we call it. But this is really, we're adding water, we're hydrating it, but we don't add the same thing to those 2 jazz hands. One grabs something different. And the reason it's important to recognize the difference between the symmetrical and unsymmetrical, it has to do with, do we need to consider Markovnikov's rule or not, which hopefully you've already read about or watched a video on, but you'll see us apply it as we go through some of the practice problems. We need to apply, or at least consider, sometimes Markovnikov's rule wouldn't matter, but we need to at least consider Markovnikov's rule for unsymmetrical addition. We don't need to worry about it for symmetrical because we're adding the same thing to both sides. Hopefully that makes sense. So let's take a look at a practice problem for each of these to kind of get to the basics of them. So first of all, hydrogenation. We're going to write the hydrogenation reaction of 2-butene. Now this doesn't specify at all what type of formulas I need to use, so I'm going to go ahead and use a line formula because I'm lazy. So 2-butene, So butene, that tells me it's an alkene. So I know I'm going to have a double bond in it. And the but tells me that I have 4 total carbons. And the 2 tells me where that double bond is located. So I'm going to 1, 2, 3, 4. Whoops, sometimes that happens. 1, 2, 3, 4. There's my but, and then I'm going to put the double bond on my second carbon, and that distinguishes it from some other structural isomers of butene, because we could have the double bond between carbon 1 and 2. So, okay, so then I have hydrogenation. So remember, I have that word here. I have hydrogen. So that tells me I'm going to be adding hydrogen. Hydrogen, like the halogens, is also a diatomic element. So hydrogen gas, which would be used for the hydrogenation process, is actually little molecules of 2 hydrogen atoms covalently bonded together. And because that covalent bond is pretty strong, this reaction requires a metal catalyst, such as platinum is a really common one. So you could write like platinum, or you could even just say metal catalyst. You know, but it's going to need a little kick in the pants. And the kick in the pants comes from, it actually needs help to break this. This is very reactive, but this would rather stay together. And so that catalyst helps it. So if I'm going to hydrogenate it, let's kind of think about what's happening for a sec. I'm going to open up. I like to do it this way, just kind of even mentally to walk myself through it. I like to scribble out my double bond and do some dashed lines. Those are now my jazz hands. You know, they opened up, jazz hands. And what am I going to add? I'm going to add one of the hydrogens to one and one of the other hydrogens to the other, because, you know, I can also think of this molecule like this. So I lose that double bond. And what do I end up creating? 2, 3, 4. I end up creating butane. So we went from a unsaturated alkene to the saturated by adding that hydrogen. Now, what's the difference between this and doing the same reaction with an alkyne? Well, that really is only one. The catalyst isn't different. The whole overall process isn't different. But because a triple bond is really, if you could almost think of it, it's like 3 single bonds, right? I mean, that's not really, but we would have to saturate it twice. I mean, we don't do it in 2 separate steps, but it's going to take 2 molar ratios of hydrogen. So for every one of those bonds we need, so it took 1 mole of hydrogen to saturate the double bond, it would take, I would want to have a 2 in front of that. But other than that, everything else would really be the same.